Just unmute. Keep unmuting. Let me just 1 second. Okay. Is this visible? I think, am I sharing the PDF? No, PDF is not shared. Let me share that also. 1 second. Okay. Is this visible now? Inverting amplifier?
Yes, sir.
Okay, fine. Let me just go to this also. Of course, we're going to have objective before you start conducting any experiment. Let us see what are the objectives of conducting this particular experiment, that is op-amp amplifiers, whether it is inverting amplifier or non-inverting amplifier. So we will going to have an objective for all of them. Just a minute. Okay, that's fine. Okay, one of the objective is to verify the voltage gain. Of course, voltage gain of the uh, okay, voltage gain. 1 second, let me just voltage gain of inverting and non-inverting amplifiers. Obtain the frequency response. Fine. One of the objective is this. How do you measure this voltage gain, Rupashri?
Sir,
How do you measure the voltage gain of an amplifier?
sir, peak to peak,
Hmm.
sir,
Peak
I
to peak
can
of
show
what?
in the
Can you tell me? Peak to peak of
vertical,
what?
vertical,
Any,
vertical
forget about the procedure. How do you measure the voltage gain?
minus GM into RD.
No, while conducting the experiment, suppose if I ask you to find the voltage gain of the amplifier, how do you measure it? Will you measure the
Sir.
peak to peak of output by peak to peak of input?
Yes, sir. Yes, sir.
Okay. And then how do you obtain this?
And the frequency response.
How do you obtain the frequency response of the amplifier? Measure DC voltage gain and 3 dB bandwidth and the unity gain bandwidth. What do you mean by this DC gain?
DC gain,
Uh,
normal voltage gain.
Okay, DC gain is nothing but it is the gain of the amplifier at lower frequencies. DC actually corresponds to zero frequency. Even if you are going up somewhere around 50 hertz, 100 hertz, that we call it as DC gain. You cannot start with the frequency of 0 hertz, but still at lower frequencies, whatever the gain, we call it as DC gain. What do you mean by 3 dB bandwidth? How do you measure 3 dB bandwidth? Now, these are the things what you should get after doing the op-amp amplifiers. So you should be in a position to measure what is the DC gain. So these are the objectives while performing the experiment. So and then you have to find what is the 3 dB bandwidth and unity gain bandwidth. What may be this unity gain bandwidth? So first, what is 3 dB bandwidth and then unity gain bandwidth? Hello, hello. What do you mean by 3 dB bandwidth? Are you there? Rupashri or who was there? Network gone. Hello.
Sir, it's breaking. I'm going to the network.
Okay.
1 minute, sir. 1 minute.
Okay. Someone else who is having a better network? Hello. Hello. Someone else? Preksha.
Hello, sir.
This is?
Hello, now I'm audible.
Yeah. Okay.
Um,
We are supposed to measure. Okay. Forget about asking you people. Okay. 3 dB bandwidth
is the
and
frequency mean?
Mm.
at which the amplitude reduces by 3 dB.
Okay, compared to the maximum gain.
The input, yes, sir.
Compared to maximum gain, where it is 3 dB down, that corresponds to the corresponding frequency at which the gain is lesser than 3 dB is called as 3 dB bandwidth. And unity
Yes,
gain
sir.
bandwidth, it is that frequency where the gain of the amplifier is 1 because it is unity.
Yes, sir.
Okay, next is determine the gain and phase margin. Okay, this is bit okay tougher side. Okay, at this point of time. Then measure slew rate. We'll measure this slew rate and all those things, and then find the saturation voltage of the amplifier. So we can actually find out what is the maximum voltage, what is the maximum output voltage does an operation amplifier can give for the applied supply voltage. So whatever supply voltage you have supplied, so what is the maximum voltage you can able to get it. So these are the 5 different parameters you are supposed to find, out of which maybe I'll just skip this, okay, gain and phase margin at this point of time because you cannot understand, okay, what it is. Let me just play you a video, so where it has been conducted just yesterday. This is how you can able to effectively conduct the experiment, and then just have a look at this. I will just keep explaining the thing. Okay, this is how you log into the remote lab, and then you'll be searching for the operational amplifier. You can see there is an op amp. Just select, there are so many experiment using operational amplifier. One of them is inverting amplifier. Click on that. You have got 9 different combinations, INV1 to INV9. Just click on any one of them. You'll get the details of all those experiments. Can you see it is inverter 1, what is the value of R1, RF, all those things are specified here, so that user can select whichever inverter he wants, and then he can able to conduct the experiment, and he can able to select any one of the inverting amplifier depending on his choice. He can measure input voltage, output voltage peak to peak, he can measure the gain of the amplifier, bandwidth, and of course gain bandwidth product he can able to conduct. Now, upon selecting a particular amplifier, he can simply press conduct button. So before he press conduct button, he should be opening the analog discovery, waveform and the scope. So using waveform, he or she should apply a certain amplitude and frequency of sine wave. Here you
Sir,
can, yeah,
hello, sir.
tell me, tell me,
Hello.
hello, hello,
Hello, sir.
yeah.
Sir, nothing is visible.
Oh, that you have to tell in the beginning, no? Now you are telling. Okay,
I was calling you, sir, but you didn't respond.
I was not listening to you. It was not audible. Okay, let me just share this. Sorry for that. Let me share it. Where is the sharing one? Somebody can. Okay, let me just share it. Okay, now I can. I think now I can share it. Where is? 1 second. Okay, I'm sharing this. One second. Where is my? Okay, is this fine now? Yeah. Is it visible? Hello.
Yes, sir.
Yeah. Of course, we are trying to conduct inverting amplifier using remote lab. Just go through this procedure. You may be already knowing it, but let us go through in detail. Okay, what are the different settings you have to make while measuring different parameters. So there are 9 different combinations, INV1 to INV9. The corresponding values of R1 and RF have been specified in the table, and because that's the circuit diagram and the corresponding values are there listed out, and student can able to apply whatever amplitude of input he can apply. He can measure peak to peak, and he can measure output voltage peak to peak, you can find out what is the gain of the amplifier, find out the bandwidth, and then of course gain bandwidth product. And once he selects any amplifier, you can simply press conduct button. Before you press conduct button, he should be opening this unlock discovery. You should apply appropriate sine wave of lower frequency of certain amplitude. You can see here I'm applying zero point 0.2 volt and the frequency is 100 hertz. Now you can see it's still not yet conducted. You're not getting any waveform over there. Now you see, I can see I have pressed conduct. Since it is INV1, so there is some corresponding value of R1, R2, and you can see it's actually inverted output voltage. The output input is increasing in the positive direction, whereas the output is going down. Blue one is corresponding to output. The channel 1 LO is corresponding to the input, and we can able to make this single window. Of course you can able to change it to different combination INV2. If you can see INV2, you have R1 and RF as same as 10 kilo ohm. The gain is actually -1. That's why I can see both the input and output amplitudes are same, and here it's a different combination of inverting amplifier. So likewise you can able to keep selecting the required values of what R1 and RF, and you can keep getting different gain of the amplifier. Okay, let us see how can you able to measure different parameters. For that you can just make this bold enough. You can make stop the waveforms so that you can able to clearly measure the waveforms. Now I clicked on measure, so it says predefined measurements. So let me select channel 1 peak to peak amplitude, and channel 2 again peak to peak, which will give me uh, the gain of the amplifier. And if you want to know what is the frequency of the signal, you can simply select horizontal and frequency. If you can see there, the input peak to peak is 0.41, output peak to peak is 2.16, and frequency is 100 hertz. From this ratio of C2 by C1, you can able to get the gain of the amplifier. And to get the bandwidth and DC gain, so what you can do is of course now here we am trying to show you, okay, by applying different shape of the waveform. Now I'm applying a square wave. Can you see for this square wave you got a input as square, output as square, Rupashri?
Yes, sir.
Yeah, now you can see I can even able to apply a triangular waveform. You can see this is triangular waveform. The input is triangular, output is also triangular, but you can see it's inverted.
Yes, sir.
Not only triangular, you can still apply a DC voltage. You can see now I'm trying to apply a DC voltage. See now this is DC. Actually the DC is now 0 applied. So let me just go back and change the DC amplitude to some different amplitude. Can you see now I'm applying 0.2 volt, and since gain is some value, can you see it is coming as negative minus 1.0 something. For that you cannot measure peak to peak here, so this should be an average voltage. So these are some of the what changes you have to make. For sine wave, square wave and triangular wave, peak to peak would have been fine, but for DC voltage it should be an average voltage. You can see I'm trying to measure the average voltage of input and output. Okay, now of course let me just, of course I'm trying to just remove everything. Do a fresh channel 1 vertical. See, this is average. Channel 2, again double click on that, you have both the values. Can you see now it is 0.2 is the input and output is minus 1 volt. Almost gain is
Yes,
minus
sir.
5.
Yes,
Minus
sir.
5 is the gain.
Yes, sir.
Okay, forget about the values of R1 and RF that have been selected there. Uh, now, now I'm trying to apply the sine wave now. I'll make the offset voltage 0. Go back to your waveform. Now you can able to see what is input peak to peak and output peak to peak. Now this is about the time response. I can able to do the frequency response also. For that I should select network. Can you see I'm selecting network now?
Yes, sir.
Now we have to carefully select the start frequency, which should be a bit lower frequency, and end
Why, sir?
frequency. No, low frequency means because I should start from okay, how does the op amp behaves at low frequency. So that's why I start from 50 hertz
Okay, sir.
because I want to measure DC gain. No, DC gain is at a low frequency, and you can
Okay,
also
sir.
see that amplitude is 0.2. It should be a bit less. If it is more, gain into amplitude input amplitude should not go above your what is that saturated voltage.
Okay, sir.
Now you can see, let me just stop this, and can you see here, this is there somewhere around this much, and you can see it is stopping here itself. So this much amount of space is being get wasted. Am I correct?
Yes, sir.
Since it is this much space is wasted, I can adjust this range. Can you see the range is 100 dB?
Yes, sir.
This 100 dB and top 20 corresponds to, can you see this 20 on the top here?
Yes, sir.
And this is minus 80.
Yes, sir.
How much is the overall separation?
100.
That's what is this
100.
100. And there is no point in having 100 dB range here because it's nowhere going down somewhere here. So that's why I'm trying to change this range from 100 dB to a lower value. Just see what happens. Can you see I'm just changing it to 40 dB? Can you see it is now 20 to minus 20?
Yes, sir.
Now I can place the cursors. I will stop it now. I'll place the cursor so that I can comfortably, even you can make it range as 20. It doesn't matter. I
Okay,
can see
sir.
I'm taking one normal. Just have a look at one normal and one delta so that I can place. You can see the first one I'm placing at a lower frequency. That frequency is somewhere around how much? 95 hertz. See here, this is 95 hertz.
Yes, sir.
The second one, you can see I'm keeping it in such a way that so that 3 dB frequency is sorry, delta y is minus 3 dB. Can you see the
Okay, sir.
corresponding frequency there? How much? 46.86 kilohertz. Here, this one. Correct?
Sir, where, sir?
This one, 2.
Yes, sir.
Just have a look at this. This is the frequency what you're talking about. 46 point. This is your 3 dB bandwidth.
Okay, sir.
Okay. You can see now I'm just it's again running over there. Now this is fine. You can able to find out what is the DC gain. How much is DC gain here? 14.6. You can also see the phase. Phase is it almost 179.9 degrees?
Phase.
Phase
Yes, sir.
179 here. That corresponds to minus 180 degree, which is an inverting amplifier. You will be treated as minus 1. Sorry, minus 1 is the this one. What I'm trying to place here is it is the frequency corresponding to unity gain. Can you see this is 0 dB?
Yes, sir.
0 dB corresponds to 20 log of 1 is 0, no?
20 log of 1. Yes, sir.
So that whatever log 1 you are writing, 1 is nothing but the gain. What is the gain then? Gain is 1, no? No. Here in this case, what is the gain here? It is 14 dB. Am I correct?
Yes, sir. Yes,
So
sir.
is the gain keep reducing?
Yes, sir.
Keep reducing. At some frequency, gain will become 1.
Yes. Gain. It's 0.
No, 0 dB is 1 because 1 is volt per volt. Please
Okay,
understand,
sir.
here we have two things. One is whatever gain you are writing is in terms of dB, and whatever gain that you are displaying here is dB. What is in terms of volt per volt? Is it not okay 10 to the power of okay 0 by 20? Hello. What is 0 dB
1.1.
corresponds to? What is 0 dB corresponds to in terms of volt per volt? Let me just show you this.
1.
It is 1, no?
Yes, sir.
Hello.
Yes, sir.
So 0 dB corresponds to a gain of 1. When I say 1, it is 1 volt per volt. Am I correct? Or am I confusing you people? Hello? Hello?
Hello.
Hello?
Yes, sir.
Is third cursor corresponds to a gain of 1 volt per volt, which is equal to 0 dB? Hello.
It is the third cursor, sir.
This one, third. At the bottom, can
Yes,
you see
sir.
this is 3?
Yes, sir.
This is third
Yes,
cursor.
sir.
Is this gain corresponds to 0 dB?
Yes, sir.
Is that 0 dB corresponds to a gain of 1 volt per volt?
Yes, sir. Yes, sir.
This frequency is unity gain frequency, unity gain bandwidth. Can you say it is 379.25 kilohertz?
Yes, sir. Yes, sir.
We have 3 frequencies. Can you just tell me what are those 3 frequencies?
96.955
Okay,
hertz.
you just find 96 hertz. That is DC gain. That is the
Yes, sir.
frequency corresponding to DC. Even you can keep it less, it doesn't matter. What is the second one?
46.
What is
What?
that
46
corresponding to?
DC.
See here,
3 dB frequency.
3 dB bandwidth.
Yes, sir. 3 dB band.
We're not keeping this 2 delta 1 at randomly at any place. It is specifically placed at a point 3 dB down from the maximum.
Hello.
Hello. Hello. Is this fine? Hello.
Yes, sir.
Okay. How about the third
It's
one? Third.
raining here, sir. It's breaking.
Okay, fine.
Third one, it's unity gain
Unity gain.
bandwidth.
The corresponding frequency is called as unity gain bandwidth.
Yes, sir.
So, do we now get to know some of the objectives? Is it being fulfilled? We could able to measure the DC gain. We could able to measure the 3 dB bandwidth. We could able to measure what?
Single.
Unity
Unity
gain.
gain.
Unity gain bandwidth, and you can also verify the phase in the passband. So phase whenever it is DC gain. Can you see the phase is minus 180 degree or 180 degree?
Yes, sir.
So because of that 180 degree,
Minus. Yes, sir.
okay,
Yes, sir.
it's not minus. It is 180 degree means okay. It is having a sign of minus.
Yes, sir.
So can you tell me what is the gain of this amplifier now? 14.6 dB at an angle 180 degree.
14.6
dB at an angle 180 degree corresponds to what volt per volt? How much? Is it a gain of minus 5.37?
Yes, sir.
The gain of the
5.37.
amplifier at this point of time is minus 5.37. Correct? Am I correct? Hello.
Yes, sir. Yes, sir.
How is that minus?
Opposite, it's 180 degree.
No. Okay, because in the phase response, can you see in the phase response it is 180 degree? Hello. Hello.
Yes, sir.
Because of this 180 degree phase, it is negative. Because of this magnitude, whatever you have, 10 to the power of 14.6 divided by 20 is the gain, which is 5.37. Correct?
Yes, sir.
Okay, we'll proceed with this. Of course, that's what I'm trying to explain over here. So these are different frequencies. You can see I'm just trying to place exactly at somewhere around close to 0. Can you see now it is minus 0.01, which is around 386 kilohertz unity gain bandwidth.
3.
Bottommost.
Yes, sir.
Okay.
Yes, sir.
Now you can say I'm just trying to change it to a different combination.
Yes, sir.
Yeah.
386.08
Fine. Now it is inverter 4.
kilohertz.
Inverter 4, if you can see here, I'm just trying to I'm conducting the experiment. Can you observe, Rupesh, here? Actually, the output is lesser than input. I can apply whatever larger amplitude also. Can you see now blue is smaller compared to the yellow one? Hello. Hello.
Not audible, sir.
Okay. Now this is a different combination of R1 and RF, so that we have a gain less than 1. We have a gain less than 1. That's why you can see the output is lesser in
Yes,
amplitude
sir.
compared to output. Sorry, output is lesser than input. And if you can see the
Yes.
Bode plot is less than 0 dB. Can you see now it is negative
Yes, sir.
magnitude? You can see now it is minus 6.51 dB.
Mine.
Here.
Yes.
This one.
Yes, sir.
Okay, still you can see the phase is minus 180 degree. Plus or minus is
Yes.
same, no? Whether it is plus 180 degree, minus 180 degree, it is minus 1. Now you can see I'm
Okay, sir.
trying to change the different combination. Now it is INV5. INV5, can you see the gain has gone up? Can you
Yes,
see
sir.
now gain is too much? You can see it is going above the scale. Now I have to change the range, volt per division. I need to change. Now these are the simpler modifications you have to. Can you see now it is clipped off?
Yes, sir.
Now when it is clipped off, you may have to go to wave gen and then reduce the amplitude. Otherwise, if you measure the gain now, it will not be proper. Before you measure the gain of the amplifier, first and foremost thing is that the output should be undistorted. Now you can say I'm changing the amplitude from 1 to 0.5 volt.
Okay, sir.
Now you can see fine. Now you should measure peak to peak of output by peak to peak of input.
Okay, sir.
Whenever it is clipped off, we are not supposed to measure because it is not a proper, you will not get a proper gain.
Yes, sir.
Okay, now of course we can certainly do the, now I can change it to square wave. See now, let me just go back there, and I'm trying to demonstrate what is the slew rate. Slew rate is actually defined as the time taken by the signal to go from plus V side to minus V side. So because now we can see, is it taking some finite time? Can you
Yes,
see
sir.
it is certainly taking some time. It won't come down within no time. So it certainly takes some time. So
Yes, sir.
it is the ability of the amplifier to switch from one level to other level is called as slew rate. Slew rate.
Right.
Ideally speaking, this slew rate should be infinity. Matlab, within no time it should swing from one value to other value. But it certainly takes some time. That's why maybe you might have
Yes, sir.
learnt in your basic electronics. Slew rate of an op amp should be infinite. Slew rate is actually written as volt per time. Volt per time. So if the time becomes 0, does the entire ratio becomes infinity?
Yes, sir.
So, but it is not so. Typically, we're going to have some what slew rate for the op amp that what we are using in the lab. It's around 0.5 volt per microsecond. That is the slew rate. Let me repeat. It is, all of you can write. The unit of the slew rate is volt per microsecond.
Volt per time.
Volt per
Okay.
microsecond. For the op amp that what we are using in this remote lab is zero point 0.5 volt per microsecond or 500 millivolt per microsecond. We can just actually measure what is that what slew rate is. So you can see how to measure is. So
So
now
500 millivolt per second, no, sir.
either it can be 500
Millivolt per second or microsecond, sir.
500 millivolt per microsecond.
Okay, sir.
No, it should take very less time. If it takes second, then it will be very slow op amp.
Okay, sir.
Either it is volt per microsecond. The
Okay, sir.
op amp. Okay, let me just write it here. Uh, just a minute. Okay, let me continue with this, and then I'll just come back to that. You can see I'm just trying to place two cursors in such a way that it will give directly what is this. Can you see here? This is del y by del x. See a last
Yes,
column.
sir.
Last column actually gives the slew rate.
Cool. Del
Last
Y
column.
by del.
Can you see it is 315 volt per millisecond?
Minus
Okay, forget about that minus.
315.2 volt per microsecond.
Forget about that negative sign. Is it 315 volt
Mil-
per millisecond? 315 volt
Yes,
per
sir.
millisecond. Can I write it as 0.315 volt per microsecond?
Point 315. Yes,
Volt.
sir. Yes, sir.
That's what. So typically speaking, in the data sheet, they say that it is zero point 0.5 volt per microsecond. So typically when I'm performing, I'm getting very close to it. Correct?
Yes.
Okay, let me again start running this. Can you see I'm just expanding it and placing it appropriate. It should be placed in the transition period, transition region. Can you see now it is 333.9 volt per millisecond.
Yes, sir.
So it cannot be placed anywhere other than this transition. You cannot place it here and then measure the slew rate. It should be in that region.
Okay, sir. How do we get to know that
What?
area,
No, no.
the transition?
We actually got this one, no? So this is, where was that? This was the waveform. Can you see this is the waveform? Or let me
Yes,
just go
sir.
one step behind. So is this your waveform? Let me just go to this square wave. Were you getting this?
Yes, sir.
Okay, one second. You are getting actually this square wave. So when you are getting
Yes, sir.
square wave, you stop it and then expand it. You can say
Yes,
I'm
sir.
going to expand it. Okay,
Okay,
just
sir.
use your cursor. Sorry, that pad in your remote. Sorry, in your laptop. You just expand it. You can place the cursors now. You can zoom in and zoom out.
Yes, sir.
Now I'm just placing it so that now the cursors have to be placed over here. One should be normal, other should be delta. Can you see this is 1 and this is 2 delta 1? This is 1, this is 2 delta 1.
Okay, sir.
And you have to measure del y by del x. Del y is what? Voltage. Del x is time. Can you see it is volt per second?
Yes, sir.
Because on y axis what do you have? Voltage. On x axis
Time.
it is time. That's what is this.
Yes, sir.
Okay. Let me just proceed with this and then try to find out. Okay, now we can place them in a different. So now the slew rate is around. Let me just see. Is it around 400 or 0.4 volt per microsecond? It's almost there.
Yes, sir.
0.4 volt per microsecond.
Yes, sir.
Or in terms of millisecond, it is also. Okay, this is
Yes,
another
sir.
objective achieved. You can measure the slew rate of the op amp using remote lab. These things are not possible in your Tinkercad. So it's very
Okay,
hard to
sir.
just make out. Let me again go to sine wave and then run it. Can you see since the frequency is a bit low, I'm just trying to, of course, I'm just scrolling it so that you will get the entire waveform. Okay, now let me just see. I can able to see both the waveforms. Here, what I'm trying to do is, I'm just trying to vary the amplitude of the sine wave simultaneously. Can you see it is now clipped off here? Hello. Can you see it is clipped off? Hello.
Hello, hello, sir.
There is an option for changing the amplitude here. You can just scroll it up or scroll it down. The amplitude, now you can see it is being get clipped off.
Yes, sir.
So you need to slightly reduce amplitude so that this clipping goes up. If you are increasing further, it just clips on either side. You cannot
Yes, sir.
measure, of course, this happens to be your, what is that, maximum output voltage. That is saturation voltage.
Yes, sir.
So you should never get this clipped off waveform at the time of measuring the gain of the amplifier. So while measuring the
Yes,
gain of
sir.
the amplifier, the output should be pure sine. It should not be a clipped waveform. Neither positive half should be clipped or negative half should be clipped. How do you ensure that it is not clipped?
Yes, sir.
reduce the amplitude of the input signal.
It's pure sine wave.
If you reduce the amplitude of the sine wave, then it will not be a clipped waveform. So this way you can able to do it for different combinations, whatever combination that is available. You can achieve all these parameters. So what are the parameters that we achieved? One is DC gain, 3 dB bandwidth, unity gain bandwidth, slew rate, and of course that gain margin, phase margin, of course that is out of scope of this particular course. So just see it maybe in the fourth semester. We'll just have a look at it. The bandwidth, we actually do it in your frequency response, that is done using, what is that, network.
Network.
In the scope you can measure what is the gain of the amplifier in time response, that to keeping the frequency at a low frequency. So frequency should be around 100
50.
hertz, 100 hertz or 50 hertz. Whereas in case of network, you start from a frequency of what is that, 50 hertz, go up to a frequency of maybe 200 hertz or 200 kilohertz or 500 kilohertz. Amplitude should be low enough so that output is not distorted.
Yes, sir.
Maybe okay. Okay. With this, of course, same procedure is followed for non-inverting amplifier also, where only difference is that gain cannot go less than 1. Here you can see for one of the combination, can you see this INV5? Can you see R1 is less and RF is so large for this inverter 5? So gain will be
Yes, sir.
maybe for this itself. Can you see here? Here the output is less compared to input. Here blue one is less compared to the yellow one.
Yes, sir.
It is possible only in inverting amplifiers where you can get gain even less than 1 or more than 1. But in case of non-inverting amplifier, the gain is always more than 1, and phases, they are in phase. So there is no phase difference between the input and the output. Correct?
Okay, sir.
Okay.
Yes, sir.
We will just maybe Chandana, we can give that access to students, no?
Yes, sir. Yes, sir.
Yeah, we'll just give the access to students. I want all of you to just
Yes, sir.
repeat this. Of course, no need to do it for all the experiments, all the combinations. Forget about what is the value of R1 RF. Just note down what is output amplitude, input amplitude, measure 3 dB gain, measure 3 dB bandwidth and the unity gain bandwidth, and of course measure what is the slew rate of the op amp. So that you repeat for around 3 to 4, maybe 2 combinations of inverting amplifier and non-inverting amplifier. So maybe 2 or 3 of you can just join one of the lab. I think we have around 3 to 4 inverting, these remote lab experiments are available, or system is available. How many of you are there? Around 14, 15. I think we have around 5 systems answered there. So let me just check it out. So then we just go to lab and then start giving the access.